Okay, so today we're going to talk about a mathematician you probably never heard of. But honestly, his ideas, they literally shape our entire understanding of reality. His name was Christoffel. And for him, it all started with one single incredibly deep question.
And it's a question we've all asked, right? What stays the same when everything else is changing? You know, in a world with so many different perspectives, different ways of looking at things, what's actually fundamentally real? Is there anything we can all point to and say, yes, that's true?
Well, that exact question completely obsessed this one 19th century mathematician, Elgin Bruno Christoffel. And his answer, wow, it led him to create a whole set of mathematical tools that, get this, would one day let Einstein describe gravity. And not just that, but it lets us map everything from earthquakes to the actual shape of the universe.
So how on earth did he do it? Well, Christoffel's entire life's work really boils down to this one super powerful idea. He was on a quest to find things he called invariants.
Okay, so what's an invariant? It's pretty simple, actually. Think about your height. Your physical height is an invariant. It doesn't matter if you measure it in feet, or meters, or inches. The reality of how tall you are stays the same. That's an invariant. And Christoffel's big bet was that the deepest truths of the universe had to be just like that, unchanging. And he took this one idea and applied it to two totally different and, frankly, chaotic worlds.
All right, let's dive into the first one, the absolutely mind-bending geometry of the universe itself.
So look at this. Doing math on a flat grid, like you see on the left, that's easy, right? It's predictable. But our universe isn't flat. We know now, thanks to Einstein, that gravity curves and warps space, kind of like that distorted grid on the right. And that creates a massive problem. I mean, how are you supposed to write a law of physics that works everywhere if the very map you're using stretches and bends all over the place?
And this is where Christoffel had his big breakthrough. He came up with something we now call the Christoffel Symbols. The best way to think about them is like a set of universal rules of the road for math. They're these little correction factors that perfectly account for the curvature of space. They make sure the laws of physics give you the same answer every single time, no matter how twisted or warped your perspective gets.
And this leads to such a great way of thinking about it. The Christoffel symbols. They aren't the words of physics. They're the grammar. They're the hidden rules that make sure that any sentence you write about gravity or motion makes perfect sense to absolutely everyone, everywhere in the universe.
And you can literally see the dominoes fall right here on this timeline. Okay, so in 1869, boom, Christoffel lays the groundwork. Then, a few decades later, other mathematicians build on his ideas to create something called tensor calculus. And then, the final piece, 1915, Albert Einstein comes along, picks up this now complete mathematical toolkit, and uses it to write the general theory of relativity. It's just incredible. Without Christoffel's grammar, Einstein's masterpiece about the universe, it just couldn't have been written.
But hey, remember, Christoffel had a second obsession. So let's completely switch gears. We're going to go from the huge scale of the cosmos all the way down to the chaotic, messy world of waves moving through stuff.
So picture this. You're trying to figure out how a sound wave, or maybe a shock wave from an earthquake, travels through something like a crystal. The problem is, the crystal isn't the same in all directions. It's lumpy. For the wave, it's basically like trying to navigate through a turbulent abyss, where every single path is totally different from the last. So that was the big question, right? How in the world can a wave move predictably through a material where every single direction is different? I mean, how do you find any kind of order in that kind of chaos? It seems impossible. But Christoffel, he had a hunch. He suspected there just had to be some hidden underlying truth, an invariant, running the whole show.
And he found it. It's called the Christoffel Equation, and it's this incredibly elegant piece of math that's basically a universal map. It doesn't matter how complicated the material is. This one equation can tell you exactly how fast a wave will move in any direction. He did it. He found the invariant rule hiding inside all that chaos.
Okay, so let's just pause for a second. We've got two completely different problems, right? The geometry of the entire universe and waves moving through a tiny crystal. And he solved them both with the exact same core idea. And this is where we get to the heart of what makes Christoffel so important.
His work gives us this amazing metaphor, something we can call the invariant gap. Just think of it as this giant gap, this chasm between any two different perspectives. And if you don't have an invariant to connect them, to bridge that gap, then two people looking at the same thing might as well be living in two completely different realities.
And that's exactly what Christoffel's work does. He built bridges across those gaps. For gravity, his invariant bridge makes sure the laws of physics are the same whether you're here on Earth or you're falling into a black hole. For the waves, his bridge makes sure the physics works no matter which direction you're looking. And here's the key takeaway. These invariants are literally what holds our shared reality together.
And what's so wild is that this 19th century idea of bridging gaps is, well, it's incredibly modern. It actually perfectly anticipates a really cool contemporary philosophical idea about how reality itself might actually be put together.
It's a framework called psi-phi theta. You see the Greek letters there. And the basic idea is that reality kind of emerges from a three-step process. And you'll see in a second, Christoffel's work just slots into it perfectly.
Okay, here's how it works. Step 1 is psi. Think of that as just infinite potential. All the possible ways of looking at the world, all the possibilities, just a sea of chaos. Then comes step 2, phi. This is the crucial part. It's a rule, an invariant, just like one of Christoffel's equations, that reaches into all that potential and imposes some kind of order. And that leads to step 3, theta, the single structured reality that you and I actually experience. So you see, Christoffel's real genius was in figuring out those phi rules, the fundamental laws that turn a bunch of random potential into a cosmos we can understand.
So let's bring it all home. Why should we care so much about some mathematician from the 1800s? Well, because his way of thinking, it's now, and I mean this literally, it's everywhere.
I mean, just look at this list. We're talking about the cosmology that lets us hear gravitational waves from colliding black holes. We're talking about the GPS in your phone, which has to use these ideas to correct for the curvature of spacetime just to tell you where to turn. Material science, seismology, even the most cutting-edge stuff like AI and quantum gravity, at their very core, they are all about finding invariance. It all comes back to this one powerful idea from Christoffel.
And if you want to boil his whole philosophy down to one sentence, this is it right here. Look instead at what remains when you change how you look. It's such a powerful idea, not just for science, but maybe for life. You know, the real truth isn't what you see from one spot. It's what's still there after you've looked from every possible angle.
And so that really leaves us with one last question to think about. Christoffel used this incredible way of thinking to bridge the gaps in how we understand the entire universe. So what about us, in our own lives? In a world that feels so full of constant change and clashing viewpoints, what are the truths, the invariants, that can bridge the gaps between us?